So our days of related rates are kind of over with for the time being, right? In some ways, today's going to be the transition from deriving, which is what calculus has been for the majority of the year for us, into the world of anti-deriving. And we're going to start putting pieces together that are going to kind of connect the two today, if that makes sense. And it might not be a clear picture yet, and hopefully maybe tomorrow then we can make it a little clearer in terms of how does an antiderivative, or what we're going to call an indefinite integral, relate to derivatives. But this is going to be kind of this first step to it. So I'm calling this linear approximations and differentials. We're going to spend more time with the differential piece of it, but what that means. It's really confused. I hate to say it this way, but I don't know. I'm confused. Wait, no. So here's what Mr. Royk's going to ask us, and start here though. I realized my first year teaching calculus here, I realized I did a poor job of explaining and talking about local linearity. I really didn't at all. And the last 2 years, actually, the final that I've given in calculus has been UNL's final that they give in Calc 1 at UNL. And I've used the same final pretty much just to share with you and show and so forth. And hopefully my source will come through again this year, and maybe we can do the same thing. But one thing, looking at old UNL finals, and we'll do a lot of practice before we get to finals in this class in May, is this word, or these words, local linearity or linearization, comes up. And my first year teaching, I did a terrible job explaining it. See, it's not a hard concept, but people are like, what is that? And it's, well, I didn't really teach them, I don't think, what it is. But I want you to have an idea what this is, because we're going to kind of refer back to it a little bit today. Linearizing, what a great word, really just means that we are trying to find an approximation using a linear function, which really aka means you're just trying to find the equation of a tangent line at that point. Have we done that? Have you done that in the past here? Have you ever in this class ever had to find the equation of a tangent line at a certain point? So we kind of have done this already, and I'll hopefully show you and explain to you in a moment of what I mean by that, and go through this a little bit more. But so as you hear these words, and maybe you won't hear these a lot today, but in the future, maybe as we hear them, maybe towards the end, if they ask us to linearize something, we just want to find the equation of our tangent line and figure out what that is. Make sense-ish? And the reason why they call it local linearity is because we are actually going to kind of zoom in at our point. So what actually happens when we zoom in at that tangent line, at that specific point on my function, the tangent line and the function actually look exactly the same. They look like a straight line. And I'll kind of show you an example of that here before we move on. So here's where today's kind of random is this first part. I wanted to include this because it kind of fits with today's stuff. You'll see a little bit. But we're not going to be doing a lot of this so much today. So could you do part A, and I'll do part B in a moment here. I'll do that piece for you. But could you do A? Could you linearize at x equals 2 that function, 15 minus x squared, or x cubed, sorry. So can someone verbalize what that means? Find the derivative. What do I want to do though? I want to write an equation. So how do I write an equation? I'm going to have to find the equation of the tangent line at that point. So writing equations of lines, what are the things I need to know? I need to know and I need to know, that's what algebra tells me. What's the point? What's the slope? How do I find slope? How's calculus find slope? So do I need to do the derivative? What would the derivative be? That was kind of painless. But what now? So Clayton, you said now plug in what though? If I plug in the point into my derivative, what is that? That's the slope at that point, right? So what is the slope at 2? So if I asked you here a question, how's my function changing at x equals 2? My function's doing what? Going up or going down? It's going down. It's decreasing. What's the rate it's decreasing at? It's decreasing at -12 units per whatever we're measuring in, right? So kind of going back to all these related rates pieces. Still not done yet though, because what's my equation now? How do I, if I know slope is this, how do I write an equation of a line? Point slope form, slope intercept form, I don't care which way. So you find it for me. What is our equation going to be? So given these two things, what's our equation going to look like? Oh, cool. Oh, I forgot I did that. Ah, that's the new. I like yellow. That's yellow. That's
It matches your shirt.
I planned that. So equation's going to look like what? We're all in agreement? Yay! Yay! Sweet. So the equation of our tangent line, right, which is again what we call our linearization of this at 2. Our equation is, we get a negative 12x, that's the slope. What's my y-intercept? 31? I think plus the 31 if we is where we're shooting for there. So that's the equation of my tangent line. Again, how do I maybe get that? Some of you did it this way. You did what did you do? You did 7 equals negative 12 times 2 plus b. So if I add that 24 over, that's where I get the 31 from. So thank you for doing that part. Here's the part that I want to do for you then. Why do they call this local linearity? Is because of this. If I graph my function and my tangent line, we actually have done a lot of this in the past. Here's what it looks like. So just watch and see. So this is my function, 15 minus x cubed, right? This is the derivative you just told me, or the tangent line that we just found, right? If I look at the graph, this is what it looks like. The blue one is my 15 minus x cubed. The red one is my tangent line, right? Watch what happens as we zoom in. Zoom in. Suspense. There it is. There's the function. There's the tangent line, right? And let's make sure I'm at 2, 7, 2, 7. So I'm kind of there, close here, as close as I can be. Let's zoom in a little bit more.
It's not good.
Deep breath. There's the function. Tangent line. Let's go a little bit more though, just for the giggles of it.
Where's it at? It's not there.
Come on, function.
It's broke.
It's doing its thing.
Sorry, sometimes it pauses here. Yeah. There's the function. There's the tangent line. What do you know about the two?
I still see some blue.
Well, I haven't zoomed in more yet, but what takes place and happens is I just keep zooming in at that location. Though, what takes place about my tangent line and the function? They are the same, right? My function starts to look like that tangent line. That's called local linearization. So I'm localizing that at the specific point, and the two take on the same characteristic. Kind of makes sense? So later on, May, as we're studying for our final that we might take, if I see the word local linearity or linearization, all that really means is find an equation of the tangent line, right? That's really what it means at a certain point. And we'll do that in a second here. I'll come back to that. Let's get to the good stuff. Here's where we're going, though. This is transitioning into chapter 5 here. Don't write this down, but this is my own little note card prop to make sure I discuss this. So far in this class, right, we just did a lot of this. Up until now, you've been looking at things like this, dy, dx, right? So what's dy, dx mean?
Derivative of y with respect to x.
Derivative of y with respect to x, right? It's the change in my y over the change in my x. It's the, what are some other ways we could say this?
The slope of
It's the slope of the line, right? Which, think of back to algebra, right? Algebra slope is rise over run. Think about this. Rise is it y's? dy, change in my y, that's my rise. And notice dx is change in x, that's my, see how that kind of makes sense? But it's the slope of my point, it's the derivative. This meant that I had a derivative, but now we're going to start getting into dy by itself, dx by itself. These things we're going to talk about are called differentials. And these by themselves take on different meanings than the derivative. And so prior to today, blah, 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 they probably have no meaning, and today they still probably won't have any meaning, but maybe we'll start to get closer to having meaning for them, though. But we're going to start looking at these pieces individually. That is where we're going today. Okay? So go with me here on this journey of what is dx, what is dy. So this may be drawn, and just as a graphical analysis here. Before we can talk about dy and dx, let's talk about delta y and delta x. And are they any different? So man, make a little sketch here. We'll use the same picture to show the differences here, if there is any differences between them. So this isn't not dy and dx. I'm calling this is delta x and delta y. So this triangle, though, you guys have seen the triangle before, right? This triangle is the Greek letter. This is the Greek letter delta. And that Greek letter delta actually means change. And so we have this change in x, change in y, and of what we're actually going to kind of look at and kind of explore here real fast. So I just randomly drew a little green curve here, little function, and I kind of already put up a couple points here, but graphically this is what the delta x and delta y look like graphically. If I pick 2 points on my graph, this is what it means. Does that kind of make sense? Between this point and that point, my x changed that much, so dx is that. Between this height and that height, my dy changed that much. That's it. Sorry, delta x and delta y. That's how they change. Make sense? We can kind of explain though, and kind of this is saying the same thing. Is delta x is just a change in my x's, and as my x value changed, I'm going to get a change in my y. And the key here that you'll notice in a second here, my delta y is how my y changes along my function or along the curve itself. And you're going to see something different in a moment when we get to dy. So that's essentially the same what the picture shows. But because of this, though, we can actually write a formula for delta y. And if I explain kind of how we get to this formula, is if this itself is f of x, again that's a y value, at this point right here, this point up here, I would actually call this not f of x, but this is actually like saying this is f of x plus whatever my change was, it's going to be that height right there. Does that make sense? So how do I get a delta y? It's just the difference between those two. You okay with this? And so one thing maybe in your notes, the picture, I put this in a box. Maybe circle this because we'll come back to this because I'm going to ask you to solve for delta y here later on a problem. How do I find that delta y? I'm just looking at the difference between f of x and then at different points, f of x plus delta y. So take a little mental snapshot. I guess it's in your notes, so you can look at your notes to see the snapshot, right? This is what delta x, delta y would look like. That's what we care about, though. We don't care about delta x, delta y. We care about dx and dy and numbers. Wait, it's calculus. We don't care about numbers anymore. It's all about letters and symbols now. True. So let's jump shift though. Let's go now. Dx, dy. Are they the same?
What?
So same picture right here, right? I think Austin mentioned this, said this, and I'm going to point this out again. What is dx? Or sorry, we wrote it before as dy over dx. So what's this ratio dy over dx mean together as a ratio? This is the slope. Slope of what? True? Slope of the tangent line? Or, what we've really been doing, this is the same thing as saying this is the derivative at that point, true? So what would dx and dy be by themselves then? They're the change, right? Change in x, change in y. But in terms of my picture though, do you see how this is going to be different? It's not with my function. You see how this is different than what we just drew maybe a second ago. Going back to the other picture. Actually, I have one where I'm kind of together though. dx, dy, a little bit different. dx actually is no different than delta x. That's the same. It's just a change in x with it. But notice what my dy though is. It's a change in my y, not to my function, but to the tangent line, right? Because it's the slope of my tangent line. So it's the rise and the run of my tangent line. And so, kind of in general though, again, dx itself actually technically is the same as d or delta x. It's just a change in my x. But dy though it's the change along my tangent line, not along my function itself. Does that make sense? Or not make sense a little bit? And a couple things again, kind of the notes. If my tangent line is the derivative at that point, which is dy over dx, if this is true, then this is true. Or I could actually write an equation for dy. dy is really the derivative times dx. Right? So if I solved here for dy, I could multiply by dx on both sides and I'd get this as an equation. And this is something you're going to start seeing a lot of today, more so tomorrow yet. A notation like this. Kind of, sort of, a little bit. And the only other thing maybe I'd add in my notes is this again. Delta x and dx, they're the same thing. It's just a change in x. It's a small change in x. So as I change my x, I'm going to get a dy, I'm going to get a delta y. One last picture on this, just graphically, hopefully this makes sense. And my last picture is just putting the two together, right, just to see the differences between the two. Right, so the differences between these two is really just this, right? Here's my differences is same function again, delta x, dx, it's just a change in my x, but what is different is dy is the distance to my tangent line where delta y is my function. So the one other thing that maybe I would add in terms of, they call this the error. What's the error between these two? Well, what's the difference between dy and delta y? It's just this distance, right? However this might be. And again, anytime we write a distance, the reason why it's absolute value, distances are always positive. We don't say, hey, I got a negative error today. We get an error of a certain positive margin. So these kind of combine together. Good? You may, I don't know, visually, yes? You going with me so far? Not, don't ever read on us yet. This is where you can say, Mr. Roy, go back and try shopping again here, and let me explain it a little bit better yet. Slow down. So it's kind of like, I go back to the other equations too, if you want to get what dy is and what delta y is in terms of each other. That's what I'm saying. So, if this is the case, you okay with that? And I'll wait here. I'm going to ask us to look at just look at an example that's going to ask us for these pieces here. So they're going to ask you to find dx, find dy, find delta x, delta y. Given actually a problem, just so you can kind of get the feel of how I'd use some of these pieces to do so. Should we do it? She'll wait. I'll wait. You guys got to tell me to slow down sometimes, right? Make up for yesterday. Trying to speed through so we have more time to not be gypped on a Wednesday of time to work. So can someone verbalize out loud, verbalize for us, what's the difference between dy and delta y? What's the difference? dy, delta y, how would you say it? Thank you, Bryce.
Delta y is to the curve and dy is to the tangent.
Delta y is to the curve, good, and dy is to our tangent line. Perfect. So, as one fast example of this, and maybe not fast, let me change this because I don't like how I wrote this. A, do that. I'll write B as this. I'll call this C and D. So really there's 4 parts here. I don't know why this thing's in the way. Let's move this out of the way here. So here's Mr. Royk's question for us. Well, we're going to answer these pieces though. So everything we've done so far today. Number 1, if I had a function sine of x, could you linearize this at x equals 1? That's really what part A is going to ask you to do. So could I linearize this at x equals 1? So could I write the equation for my tangent line at 1? And then part B then is, could I use that to approximate an answer at something really close to 1, like at 1.02? Then we're going to get into sorry, let me write this nicer for us. Yeah, is there a delta character? Or no, in your keyboard, is there shortcuts? They have a hidden within. So, first step, could ask this first step, how would you do part A? How would you write an equation of a tangent? How do I linearize this at x equals 1? What am I doing? I need to find a y value. So part A, can I find a y value? So we need to find a point. How would I find y? If x is 1, how do I find y? Plug it into what? Plug it into my function, right? So if I take my function, plug it in. The only thing I'd argue, make sure your calculators are in radian mode though. So just, I don't know if, I'm assuming they're probably still there, unless your calculator's been reset for some reason, but make sure in mode you're in radians, otherwise your results aren't going to be the same as what they should be. What's my y value? 4 decimal places, what would it be? 0.8415? Is everyone okay with how they got that? What else do I still need to know though? That's my point. I need to also know my slope, right? How do I find slope? Drive it and plug in x. What's x again? 1. So what's the derivative of sine? So what's the derivative at 1? What's cosine of 1? So what's my slope going to be? So could you write now from here, could you write an equation of a line? That's the question, right? So we go back now, it's algebra again. Most of us do point slope form, I think, right? That's what I look at some of your guys' work as you plug in. They might use, actually no, use slope intercept form is what most of us are using, right? Is what I meant to say. Anybody doing point slope form? Gives us the same thing. Either way. I know this already though, right? This I know is this, because that's my slope, x. What's my y-intercept going to be here? So, what's my v? What's the rest of my equation?
Plus b.
3012.
So 0.3, oh, 310?
Oh,
3012.
Why did I write this down? Oh yeah, 0.30112. So that's what we call linearizing here. Now if I use this linearization, anybody know how would I do part B then? The change is going to be is going to end up being this, right? This change of between 1 and that is that. And maybe if I wrote this like this is how you kind of see it, I guess, but it's kind of confusing to say this. If I want to find out my approximation using this right here, what do I want to do with my 1.02? I want to plug it into my tangent line because that's my approximation. That's my way to locally linearize it, what it might be. So you kind of want to, even though it says f of 1.02, you really, as it has to approximate, what's that plugged into y here? What kind of y value do I get when I'm at 1.02 using that? So if I plug into this, I end up with how much? I don't know if I wrote this down earlier. Should be, actually it should be close to,
You subtract it, you don't divide. You're not multiplying.
5403 times, this is 1.02 plus this, I'm going to end up with, yeah, it should be something 0.8, right? So 0.8. 2.3?
Yep.
So this is our approximation, and we should approximate of what the y value would be given that point.
Yeah.
Kind of following that? Now here's the fun parts. Fun parts. If this is fun, then all by any means. How in tarnations do I find all of these guys?
Well, dy or no, dx and delta are the same thing.
Do the easy ones. So I need more room here. Can I see all these things at the same time? I wish I could. So Amanda said this is delta x is the same as dx, and I kind of wanted to say this. What's the change in 1 and between 1 and 1.02? The change is, so both of these are going to be the same. So delta x is dx x. You okay with that? Now, how do I find the? How would I find d? What do you want to do, d or delta y? Let's do delta. How do I find delta y, not dy?
The first y we found and the last y we found.
Let's see. Is it the difference between those two? So delta, though, go back to what's the equation for delta? Delta y. What's it say? Delta y is the difference between f of x and f of x plus delta x, right? So if I go back to this problem, wherever it might be hiding here, this really is, what again, f of x plus delta x minus f of x. So what would that look like for our problem? This is going to say f of what? What's x? X is 1. What's delta x? So this is really like saying f of 1.02
Which is
minus Now is this though, go back to, because here's the one thing what you guys, some of us you were saying is this guy right here, this is not, this comes from my, this isn't delta x, right? This is coming from my, kind of almost like dx in some ways, or dy in some ways, right? So I have to go back though, what is, again, my function? My function is sine, so what is sine of 1.02 minus the sine of 1, which we already know, kind of know what that is. Right, because f of x was sine of x. So what's f of 1.02?
It's 0.8521 minus 0.845.
So 0.0, difference would be 0.0106. So there's not much difference there, right? And that's kind of good, because x is small. There's not much difference. Last but not least, though, how's dy different, though? dy, go back to the formula, dy is derivative of x times dx. Do you know those things?
Derivative of x is
What's the derivative of x at 1, right? When x is 1, derivative is what? What's the slope of our... So 0.5403 is, that's the derivative at 1. What's dx? 0.02. If I multiply those two together, I get
0.0108.
0.0108.
they got on the air.
Now we just got a funny error. How far apart are these? Because they should be different. Oh, do they have to be different? The only time they wouldn't be different is if your function was a line. They wouldn't be different. They do the same thing. How would I find my error now? Part D, last piece. Where's my error come from? Again, my error comes from. All this is just the difference between dx or dy, sorry, and delta y. It's always positive, so, oops. So what is this error? What's the difference between these two?
0.0002.
So without even doing, yeah, bless you, what's, that, bless you. Right? Because the difference between this and this is just, is that 2 10,000ths units off? In statistics, they would ask you to write this as a percent, so what's our percent error? Our percent error would be 0.02%, lose the decimal 2 places, so 0.02, but here leave it right out. That's Christmas shopping in a nutshell. This kind of confusing a little bit, right? It's a little bit. Here's where you're gonna start feeling better. Give me 1 moment here. Life will get better here. This is kind of relating some of these pieces, but if you use those formulas, you can kind of piece things together and find out what these have to be a little bit. Here's what the majority of your assignment is going to be, not so much this. So Megan's looking. So Megan, talk to me here. How are we getting this? No.
I'm getting the same thing but negative. Is it
For this, because it's going to be the absolute value of whatever you get. So it's always going to be a positive error. So that's better, then, right? And again, Megan, why? It's because it's always whatever that difference is, but positive. Here's where life gets good. Let's do this. Here's where life gets easier now. Here's where the cloud is lifted from us. Maybes. Most of your assignment today is going to look a lot like this. And you're going to say, well, number one, what are we doing here, Mr. Mike? But in a moment here, you'll catch on to what this is going to look and see. They're going to say what y is. They're going to give us a function, e to 3x, cosine x. But instead of looking at a graph, finding all these other pieces like we just did, I just want to know what's dy. Now, I would argue the only thing we kind of know how to find is where dy comes from. Dy dx is what again? That's the derivative of y with respect to x, right? So if I want to get a dy, what I have to do is I'm going to have to derive what this is, right? So go back to related rates here. What's the derivative of y with respect to x? What's the derivative of y with respect to x? How would you write that? There's 1 what though? 1 dy dx, right? So this is a dy dx, true? The derivative of y is dy dx. Now, if we do this though, what's the derivative of the other side of this with respect to x? That quotient rule, Ryan. You could, Ryan. I want to see the quotient rule, Ryan. Let's do it. You could, right? It's cosine of x over e to the negative 3x. So you can do it. How would I derive this though?
E to the 3x times 3 times cosine x times 3x times cosine.
I love Rice. I'm getting slowing down here. Plus, I heard a plus here.
No, he said times. I said plus.
He said plus.
You said times.
Plus, so then what goes to that second half Rice? E to the
3x times
And we're going to want to simplify this, though. If I simplify this a little bit, again, oops, dy dx, Mr. Roy, matters. So what's this simplified, though? 3e to the 3x. What else could I kind of do to clean it up? Minus, maybe.
e to the 3x.
Right? One issue, though, right? This was not totally hard, right? Here's my one issue. What did I solve for? I have the derivative here, right? Sitting right there, dy over dx. What do I want to know? I want to know dy by itself.
Multiply dx.
How do I get dy by itself? So, my answer it's going to look a lot like, really like this, right? What's my answer going to look like? It's going to be, what is dy? Well, dy is, it's the derivative, but now at the end of all that, times dx. That's the answer. So is this much different than how we derived in the past? No, it's just that we're going to write it in this notation. And technically I should put a parenthesis because it's this whole entire thing times dx. It's not just the last part times
So if you were
dx.
trying to find dx, you would divide by dy. No.
From here, no, I'd have like a flip of it in terms of, right, I'd have to do a little more with it.
So why we do all this stuff before?
You'll see, this is going to be a little bit of notation of where we're going to go here. We're still getting there yet. Hang patience. Unmas, you just showed me real fast. That made sense. And then the last little piece of it, and then we'll call it a day here. It's Wednesday. We have some time to get a little of this done in class. So do the same thing. How would I find dy if this was my function, y equals this? And as much as we don't like to simplify, try simplifying these, please, because they're not that bad. It's not like some. The reason why I'm having you solve for dy is so tomorrow I want you to be able to look at an equation that has something dx in it and understand kind of what that notation is going to mean for us tomorrow. And this gives us that notation if we set it up this way. What do we get though? Simplified out.
I got
I think that would work. Where does it come out to? What Austin do? Oh, Austin did that. No, what did you do, Austin?
I found it yourself.
It was 3, all this stuff.
And I also found a funny video called Bill Nye's Quickscope.
Oh,
That's
basically I'm not able to distribute.
And
that
it's
over there.
hilarious.
Unless you wanted to put it out.
Pretty similar.
No, you were good. I just wanted to. One second.
I figured out what I was trying
That makes sense.
Why you cutting it?
I'm seeing.
I know I'm educated, yes.
Do it except for now, not plus though, just times though. Times the inside derivative. Are we okay with this? What's the derivative? Derivative, disagree, right? Go back, remember how to drive. The 3 comes in front, all this stuff to the 1 less power. But then what else I still have to do? Times the inside. What's the derivative of the inside? 5. If I simplify this, how could I simplify it? It would just be 15x to the 4th times x. Yay?
Yes. Yes.
And then if we want to solve for dx again, what's that? Where's that? Or dy, sorry, the dx has to be at the end. Just really deriving is all we're doing, but writing it this way. Last thing today then. I know I said that I lied, didn't I?
But wait, there's more.
Last thing, there is more. For all 1995, you get one more piece here on our shopping trip. So you don't get one of these, you get the opposite of this.
You
Though.
keep it.
What if they gave us this as, if this is the answer, if they start with this, how do I go back and write it like this? I'm going to have to undo deriving, and we're going to have to anti-derive. And today's going to be our little crack into or break into anti-derivatives. We'll do a lot more of this tomorrow and the days to come. Soon you will forget how to derive, and the only thing you'll know how to do is anti-derive. But here's how this is going to look, though. And again, notation is going to kind of matter. This will make more sense tomorrow as we do more of it. If dy equals that dx, can we go backwards with it and anti-deriving. So if you go backwards with me, right, backwards through this again, I would want to, for how do I get rid of my dx on this side? I want to, I'm going to want to divide by, so I mean everyone agree that I'd get back to this step, dy over dx equals my function, which you might say, well that's no different, Mr. Roy. If I took an antiderivative of a derivative,
Plus C.
what's the left-hand side going to turn out to be? If I take an antiderivative of a derivative,
Why?
this is just going to be y. Now this is going to be the hard part for a while. This is a little bit of thinking today is going to take place is, what's the opposite of deriving? Again, how would I work this out? Opposite of deriving.
6 times.
Normally when we derive, we always take our power in front and take one less. If I anti-derive, I want to not take away one from my power. I want to add one to it. So if this was x to the 7th,
Plus C.
Can't forget plus.
we can't forget plus c, how true. Would that work?
Yes.
Would we be done?
We're
done.
Right, again, can we check this again if we wanted to? The derivative is 7 comes in front, x to the 1 less, right? C goes to 0, so would that be where we started? Show me the bottom one, we'll call it a day, but part of the assignment today, half of the assignment today is going to need to be a little practice anti-deriving. They're going to set them up like this first because that's going to be, again, some notation that we're going to get into tomorrow. But how would I do something a little bit more complicated? And I know some of us are not going to like this at all because you have to think backwards, and we'll start learning rules here tomorrow about how I can anti-derive and make it a little quicker and easier. But for today, it's going to be kind of trial and error, guess and check.
Plus C. Think about it. You know that has to be 1 power.
So yeah, I always think in terms of first as you're starting to think always of your powers first though, right? So I know that when I do this, anti-derive this, I know that I'm going to have something to the, this whole thing to what? Something to the 6th power, right? So I start there, and if I'm not sure what else to do then with it, if I were to go through and derive it just to see what I get, the 6 is going to have to come in front, so I'm going to have this 4x plus 3 to the 5th now.
Yeah, so where the 6?
But then times what though?
1/6.
Times the 4 inside, because that's the inside. So obviously, is this the right answer? No. I need to somehow get rid of this 6 and get rid of this 4. How do I get rid of the 6 and the 4? Is I need a what on the bottom? I need a 24 on the bottom, and so technically I need, I can't do that. Technically I need a 1 over 24 here, right? Because if I were to have this constant of 1 over 24, what would happen when I took the derivative? This 6, this 4, and the 24 are going to cancel. And I'd be left with what I wanted. So I always do my power, you always go, 1 power more, but then almost in some ways take the derivative and see how you have to adjust to anti-do whatever you have, right? And the only thing I'm still forgetting though is plus C.
How does it not work?
So again, try this if you're not sure about your answer again. The 6 comes in front, all this stuff's in the 5th, but then times the 4, the 6 and the 4 are going to cross with the 24. This is going to be kind of awkward today, but half of the assignment today is going to be just practicing anti-deriving. And my hope is as you practice anti-deriving, you're going to start to learn some rules and tricks because you're going to have to. I mean, there's no way around it. Okay? So this whole shopping trip here. I shortened this a lot actually. One time I was like 3 through 4 is what I wanted. You might say, ooh, so what? The hard one is 3, 4, 5. And some of these are the harder ones. 7 is the only one I'm going to ask you to do. That's a little bit more of an application. Find delta x. 9 through 40 are going to go pretty fast. 9 through 20, I think it's 25 is all just driving. I guess I take the derivative. 26 through 40 is just going to be then anti-driving. We're about to be a little practice.
Odds.
Not right now, no.
Because I did do.
And if you want to come back to 7, or maybe some of you want to knock 7 out right away, 7 is just an application of business stuff here to look at.
Go back to the.
I will.